Hi, I'm Jaylin, and today I will present dynamic programming decomposition of static risk. At the beginning, I will explain a little bit about our setting of MDPs, and then I will explain static risk averse MDP. I'll explain what is the objective, what are the challenges, and how are people solving it throughout the years. More specifically, this work is on analysis for the dual representations, and we show that this dual method could fail for CVAR and EVAR during policy optimization, despite they are very popular this decade. The setting we assume in our paper is undiscounted finite horizon. However, a lot of the theorem can be extended to discounted infinite horizon. Beyond expectations, we will be focusing on VAR and CVAR for these presentations, but in the paper, there will be analysis on EVAR as well. In standard MDP, your goal is to maximize expected cumulative reward, and you can solve it with value iterations by starting with t equals to capital T and then backward to capital T minus 1 and iteratively all the way to 0. If you solve this Bellman operator iteratively, you will get your optimal value function as well as your optimal policy. The reason you can do this is because you can write your maximum over expectations over the joint distributions as maximum over the conditional expectations. And in that way, this will be Vt plus 1, and you assume Vt plus 1 is optimal, and therefore you can act greedily at V time t. However, you cannot do this for risk measure like VAR, CVAR, and EVAR. This is because they don't satisfy this tower property. When you nested them in a dynamic risk, it's not equivalent to the objective we are trying to solve as a static risk-averse MDP. There is two lines of work that is commonly used to solve this risk-averse MDP. One line of work augment the state space with cumulative reward or target value. Another line of work augment the state space with risk levels. And we'll be focusing on this second work and analyze them. The second line of work is motivated by Flood and Feature. In 2012, they introduced this extended conditional form of coherent risk. We'll use CVAR as an example. So what it says is you can write CVAR as a function of conditional CVAR. Note that we only use reward here instead of cumulative reward, but you can extend it with cumulative reward. What it says is you can write CVAR in terms of conditional CVAR, but your risk level has to change. So what they do is optimal when you're considering policy evaluations. So there is no optimizations. But in MDP, normally we're trying to maximize some sort of policy over these risk measures. A lot of the work has been trying to utilize this finding for policy optimizations. So instead of A, you are now looking at pi of S. And what you need to show to use this in the value iterations is you need to write max of CVAR in terms of max of conditional CVAR, which a lot of them does. And they thought that the left-hand side is equivalent to the right-hand side. Unfortunately, in our work, we show that this is not true because when you move the max into the min for the first time, you get this inequality from duality gap. So to visualize it, we will call this theta, and we will visualize max min of theta compared to min max of theta. When we compare them, we can see that this purple dot is above the golden pentagon. What it means is that if you use this dynamic program, you will overestimate your value functions. And when you use it in an MDP, this is your calculate optimal value functions. And this is a true optimal value functions. And when you deploy it, your performance is actually very bad compared to the true optimal value functions. This is because you overestimate some suboptimal or some really bad policy. And then when you actually deploy it, you realize they are really bad. However, inspired by Lee, you can also write VAR with extended conditional risk. And the cool thing is now VAR can be used in optimizations. So we will show how VAR is different from CVAR. But the most important idea is that in VAR, the zeta optimizations is over a supremum, and in CVAR is over a minimum. So when you do policy optimizations, when you move the max inside the supremum, you will not get duality gap. Furthermore, you also have to move the max inside of the min S, and according to Shapiro interchangeability property, this will also not have duality gap. As a result, you can write max of VAR in terms of max of conditional VAR. And this is very useful because now you can derive a Bellman update that is accurate for your static VAR objective. As a summary, for policy evaluation with risk decompositions, you can do it with VAR, CVAR, and EVAR. But if you want to do policy optimizations, you can do it with VAR with risk decompositions. But for CVAR and EVAR, you would overestimate your value functions. And we suggest people to use the primal decompositions, which is explained in Borley and Howe. These are the reference, and thank you very much.